Bé, molt bona tarda a tothom. Bona tarda de nou. Estem tots preparats i preparades? Bé, deixeu-me donar la benvinguda al doctor Brian Butterworth i a la doctora Emma Hayu Thomas. Ells ens parlaran de dislèxia i discalcúlia, dos trastorns específics de l'aprenentatge que tenen una incidència molt alta no només en la població catalana, sinó a nivell mundial, i que afecten de forma molt important a tot el procés d'escolarització. De pensar que els nens i nenes que tenen algun d'aquests trastorns no tenen les eines suficients per fer front a les demandes que se'ls hi plantegen i això els estira cap a la part baixa de la corba, de la taula de percentils. Els nens i nenes que a primer educació primària estan en aquesta part baixa, si no fem res, hi són a segon, hi són a tercer i així fins a sisè. I això els dona menys possibilitats inclús després de tenir èxit, o com li vulgueu dir, en la seva vida quotidiana, en la seva vida professional. Avui tenim la sort de tenir a dos referents en aquestes temàtiques, en aquests trastorns. Podeu aprofitar l'ocasió perquè els teniu cara a cara, per tant, quan acabin d'explicar-vos el que us volen explicar, feu tantes preguntes com pugueu. I ara, si m'ho permeteu, vaig a fer una petita descripció del perfil de cadascun d'ells. El doctor Brian Butterworth és actualment professor emèrit de Neuropsicologia Cognitiva a la University College of London, professor adjunt a la National Cheng Chi University of Taiwan, investigador a la Melbourne University of Australia i consultor de recerca a l'Institut Italià de Venècia i l'Ospedale San Camillo Instituto di Ricovero e Cura a Carattere Científico. Com veieu, no perd el temps, està molt ocupat aquest senyor. La seva carrera acadèmica i científica és molt àmplia i comprèn universitats i centres de recerca d'arreu del món. Compta en centenars de publicacions científiques, però a més d'aquestes es destaca per ser un gran divulgador, en fer arribar la ciència i la neuropsicologia a tothom. M'agradaria destacar la seva web, The Mathematical Brain, on hi podeu trobar un ampli resum de les seves aportacions. Al meu entendre, dues de les més importants, no sé si ell potser farà algun matís després, són un manual que es diu Dyscalculia Guidance, que tots els que ens dediquem a fer diagnòstics, a intentar reeducar la discalcúlia, ens ha servit com a referent. I un de molt recent, en col·laboració amb altres autors, és Educational Neuroscience, un text que segurament hauríem de tenir tots nosaltres com a punt de referència, almenys els que treballem en neuropsicologia infantil, perquè és un llibre que planteja l'educació a partir de les fites del desenvolupament cognitiu i cerebral i com hauria de ser a cada etapa els aprenentatges s'han de donar en base a el que el cervell està preparat per fer. Actualment el seu treball científic es dedica a la investigació de la genètica de la discalcúlia, un camí que no és fàcil i que de ben segur li planteja encara molts reptes.
Right, well, thank you very much for that introduction, Josep. It's very late in the day, at least it is for me, so I'm going to start by giving you my take-home message. So those of you who really want to go home are very welcome to do so. If you want to sleep through this talk, and so you're alert for Emma's talk, you're very welcome to do that as well. But before I start, let me thank you all for inviting me to this really interesting meeting. So this is my take-home message. There's a specialized neural network for numbers and arithmetic in the parietal lobes. Acquired dyscalculia is a result of damage to this network, and this can affect patients' ability to live an independent life. If you can't manage your bank account, if you can't shop competently, if you can't work out what the best deal is, then you're going to have a problem. Developmental dyscalculia. Here the network does not develop normally, and this is a serious handicap. Poor numeracy is more of a handicap in the workplace than poor literacy, at least according to a very large-scale UK study. And men and women, age 30 in this case, with poor numeracy have poorer educational prospects, earn less, and are more likely to be unemployed, in trouble with the law, and to be sick both physically and mentally. Both acquired and developmental dyscalculia require specialized intervention. Okay, that's the take-home message. So if you want to go home, as I said, you may. Right, acquired dyscalculia. I thought I would talk about this because this is a neuropsychology meeting, and I thought we ought to do some serious neuropsychology. And let me start with Salomon Henschen, who was a Swedish neurologist working in the first half of the 20th century. He studied a very large number of cases, and he documented them very carefully. And he found that if you have damage, particularly to the left hemisphere, that we also looked at the right hemisphere, you often get both calculation disorders and language disorders. However, he also noted that there were many patients in his case series who had calculation disorders without language disorders, or language disorders without calculation disorders. He also had a look in more detail at some of the aspects of calculation. For example, he observed some of the modularity of the calculation system. So in 122 cases of word blindness, 71 of his patients could read digits. And he thought that because you have both this co-occurrence and this dissociation, the areas are close together in the brain, but actually can operate functionally independently. Half the cases of word agraphia were able to write digits, and he paid particular attention to somebody else's case, Touche's case, in which a patient had digital alexia and agraphia, but could calculate from spoken instruction. So these input and output systems are separate from the central systems for doing calculation. This is terribly interesting and important work, and is, I'm afraid, now largely neglected, partly because he wrote in German. So I'm just going to give you a few footnotes to Henschen. So this is a couple of patients that we've reported, which show the independence of calculation skills, numerical skills from language. So CG, a patient that we described a long time ago, had large left parietal lobe damage following a stroke. The patient was well educated, was very competent in bookkeeping, that is, keeping the accounts of the family hotel before her stroke. The rest of the brain was largely okay. Her language was completely normal. Her reasoning, which we tested very extensively because we thought we would look at Piaget's prerequisites for numbers, that was entirely intact. But she couldn't count beyond 4. She couldn't use numbers at all beyond 4. She couldn't even recognize numbers beyond 4. So if you put out 5 things in front of her, this is an Italian patient, she would say uno, due, tre, quattro, and then she'd point to the 5th object and say, la mia matematica finisce qui, my mathematics finishes here. Now we discovered a kind of double dissociate of that case, patient IH, who had a degenerative condition. It wasn't Alzheimer's, it was another condition, another degenerative condition. His left parietal lobe was largely okay, but the rest of the brain was degenerating, particularly the temporal lobes. So he had very, very severe language problems. On an object pointing task where you had to point to a named object, he was at chance, and his spoken language consisted largely of stereotype phrases. We couldn't therefore test his reasoning. However, his written calculation, including multi-digit multiplication, multi-digit division, was flawless. It was without error, at least in the stages when we first started to test it. After a while, even his calculation started to break down, but in interesting ways. Here's some examples of modularization of the number system itself. So, for example, there are patients, let's see if I can get this point, there are patients who know that these are arithmetical signs, but don't know what they mean. So they might multiply when they see the addition sign, or add when they see the multiplication sign, or subtract when they see one of these signs. So they're at chance, but they can carry out the calculations that they decide these signs mean without flaw. DRC was a seminal patient described by Elizabeth Warrington, and this patient could read the signs, but he'd forgotten all his facts, so he had to work everything out. But his conceptual knowledge of arithmetic was very good. MT, described by Girelli and Delazza, this patient was pretty well intact, except he didn't know how to do multi-digit subtraction. And he had a little bug in his subtraction process. DA, let me skip over DA, but JG was another patient described by Delazza, and this patient could remember her multiplication tables, but didn't have any understanding of what the numbers meant. So if you asked her what's 4 times 8, she would say 32. And if you say, well, what's 4 plus 8, she couldn't do it. B, by contrast, had forgotten all his multiplication tables, but could work out what 8 times 7 was by using what he understood to be the principles of arithmetic. He could do his 10 times table, obviously, because it's just a question of adding 0. He could do his 2 times table, because that's just a question of adding 2 numbers together. So he could work out 8 times 7, well, that's 10 times 7 minus 2 times 7, and he could work it out. Arithmetical operations, at least in some patients, seem to be separable in the brain. So I'm not going to go through this in detail, but here you can see some patients are good on one of the operations and bad on the others. Others are bad on that operation, but good on the others. So at least in some brains, we don't know if it's true for all brains, you get this modularization of the calculation system. Going back to some of Henshin's observations, reading and writing numbers. Some patients can read numbers but not words, other patients can read words but not numbers. We had a very interesting patient, IH, who you've seen before. IH was very interesting. He could read digits, because as I said, his multi-digit calculation was without error. He couldn't read very simple words, like cat, but he could read very irregular number words, like 2. I mean, there's no other word in English which is spelt like that. And he read that correctly. He could read F-O-U-R, which is 4, but not F-O-R, which is also pronounced 4. This was a very extraordinary study, and we published that a long time ago. Now, as I said, if you have these problems, and they can be very various as you've seen, you need, as a clinician, to be able to assess for it. And we've developed at San Camilo, which Josep mentioned, a test called Numerical Activities of Daily Living, which you can find. It's free, and there's a protocol, and you can use it. And what it does is it gives you a quick clinical interview to see if it's worth doing a formal test of the patient. If you think it is worth doing a formal test, then it gives you the formal test. So you can see whether the patient is good on different operations, understands the principles, understands the procedures, and so on, all the different aspects that can break down that I've shown you. And in a paper that's coming out shortly in Cortex, in mild cognitive impairment, what we found is that differences in grey matter and white matter in the MCI patients, but not in controls, correlate with the NADL score. So if you're better, if you're an MCI patient who's good on our tasks, then you have more grey matter volume, and on a particular task, a money test, then there's this interesting white matter volume relationship with how well you do on the money usage task. So in this area here, you find greater white matter volume if you're good on money, and less white matter volume if you're bad on money. So how do we rehabilitate these people? Well, we've been working on that. So the first thing you have to do is you have to see what the patient can do and what the patient can't do, and then, for example, by using NADL, and once you've decided that, then you should focus on training that patient. So if the patient can already do addition, you don't need to train them on addition. If they can't do multiplication but can do addition, then you need to train them up on multiplication. Exactly what pedagogical principles you use for doing the training is something that we can talk about. And I'll talk about pedagogical principles in relation to developmental dyscalculia, which I believe is next. Okay, but in order to understand about what developmental dyscalculia is, you need to understand the cognitive basis of arithmetic. And arithmetic is about sets and numerosities. So here's a set. Remember this, because there's going to be oh, I didn't mention it. There is going to be a test. Because this is a talk about maths, there has to be a test. In fact, there are going to be a couple of tests. And so just in case you're not asleep, you can take part in the test. Here's a handy set, which you can use at least when you're learning to do calculations. And here's somebody using this handy set in order to do some calculation. And one way in which you can think about developmental dyscalculia is to ask, what's the starter kit that the learner brings to learning arithmetic when he or she comes to school? So of course you've got a number of domain general capacities, such as working memory, reasoning abilities, language, and so on. But there's also what I've called the number module, which is an inherited core capacity for processing numerosities, i.e. for recognizing the number of objects in a set. And there are ancestral versions of this in other species. Chimps, mammals, large and small, reptiles, fish, insects can all recognize the number of objects in a set. And if I'm ever invited back here, I will talk about my recent work on the numerical abilities of fish, which is really very interesting. And this system is adaptive for these creatures in foraging, mating, deciding whether to fight or flee, and for navigation. Individual differences in the number module are reflected in differences in arithmetical development, at least in humans. We haven't really done this very much in our animal work. Okay. Testing for individual differences. Okay, you ready for a test? Are you ready for a test? Don't all speak at once. So what I want you to do is just shout out in any language, Catalan, Spanish, English, or any other language, as quickly as possible the number of dots on the screen. Okay? Ready? You have to do it fast. This is a timed test. Okay, right. So you probably got the idea that the more dots there are, the longer it takes you to give the correct answer. Those of you who gave the correct answer. And there's a well-known curve that relates the number of dots to reaction time, and some people have divided up this curve, this is number of dots here, reaction time there, into two different processes, a subitizing process where there's a shallow slope, about 50 milliseconds per item, and a counting or estimating slope where it's about 250 or more milliseconds per additional item. And there's a point where the slope changes. And there's a basic RT, that's how quickly you can say 1 when there's 1. That means if we take a sample of these of people doing this, you can see whether your individual subject is within the normal range for this task. And as you can see, it doesn't really depend very much on education. It's fairly education independent, at least in Europe. I mean, I also do tests of the numerical abilities of Australian Aboriginal kids, and most Australian languages don't have counting words. So if you ask them how many dots, they can't say. They don't know what how many means because there isn't a word for many, and they don't have a word for four, so they can't say how many. So if you want to test them, you have to find another way of doing it. But let me just tell you now, I'm happy to explain this in more detail. These children who are brought up without counting words and without counting practices have exactly the same kind of numerical capacities as kids who are brought up in Melbourne speaking English. Okay, so let's have some more tests now. Which side has more squares, left or right? Again, in any language. A timed test, you have to be quicker. Okay. We can do the same with number symbols. Just shout out you can do it left or right, but just shout out the larger number as quickly as possible. It's a timed test, you have to do it faster. Okay, very good. Now, this is called number stroop. I have a whole other talk on number stroop and how the brain deals with stimuli like that, but I don't have time to talk about it now. But the important thing to know is that we can use these stimuli to ask two sorts of questions. You can ask of an individual, how good are they at making this comparison in terms of numerical magnitude, how good they are at making a physical comparison, which of these two numbers is physically larger. Because one of the things we want to know with these tests is this individual slow at everything or just slow at number tasks? And there's something called the distance effect. So the more different these stimuli are, this one or that one, in terms of their numerical magnitude, the quicker you can make that judgment. So if it's 9 versus 1, you're quick. If it's 9 versus 8, you're slow. And this is the other test we can use. Okay, so these are the critical tests that I'm going to be talking about. I'm going to be mostly talking about shouting out how many dots there are. And because I think this is a fairly direct test of the efficiency of the number module, and it's relatively free, as I said, of education. Okay, so now this is just something that my colleague Karen Landl did using these kinds of stimuli, and she was looking at dyslexia and dyscalculia, and this is the reaction time. And these were children, I can't remember how old they were now, but these are the dyscalculics, and the ones with both dyscalculia and dyslexia, they're very slow compared to the controls and the dyslexic kids. The dyslexic kids are not impaired on this task. Okay. So it looks as though the dyslexic's number module can be entirely unimpaired. And let me show you how predictive this very simple test, the dot enumeration test is. This is a longitudinal study. We started off with about 220, 230 kids. We tested them 7 times over 20 cognitive tests a time. And in spite of that, we still had 159 children left at the end. We had item-timed calculation, dot enumeration, number comparison, both adjusted for simple reaction time, because we want to know whether children are slow at an individual child is slow at just making a binary decision, or whether they're slow just at numerical tasks. And we had working memory tests and Raven's colored progressive matrices. And so this work is already published. Now, we don't use norms. We had a really, really nice talk earlier on today about norms and how norms are going to vary from country to country, from educational level to educational level, and in terms of ethnicity. So we take a completely different approach. We say, theoretically, what do we need to know, and what does the data look like? We're not interested in arbitrary cut-offs, 1 standard deviation, 2 standard deviations, the bottom 10 percentile. What does the data actually look like? And to do this, we can use cluster analysis. So we want to know, since children all improve, is whether they improve relative to their peers. And so norms, what norm would you use? How do we know which child is dyscalculic? Is the bottom 5%, bottom 10%, bottom 17%? None of it makes theoretical sense. So we use a cluster analysis, and we say, is there a particular cluster that picks out kids who are very bad? And then we can ask, is the learner always in the same cluster? And I'm going to talk today about clusters based on the parameters of the dot enumeration measure adjusted for basic reaction time. We've done the same thing for number comparison and get much the same result. And it turns out, because we tested these kids doing dot enumeration 7 times, at each age there were exactly 3 clusters. Now, those of you who know about cluster analysis know that it's not necessary that you get the same number of clusters if you retest the population over and over again. So we were, if you like, lucky or smart. We got 3 clusters at each time. And we're calling these clusters slow, medium, and fast for reasons that will become clear. And the clusters are very stable. And these are the clusters here. This is number of dots along the bottom. This is reaction times on the vertical. And these are the ages. You can see that even in the slow group, they start off very slow relative to the other 2 groups, but they improve. Medium group is better than the slow group, and the fast group is better than the medium group. And also, if you look at the subitizing range at age 6, so we start in kindergarten, so the oldest age in Australian kindergartens is 6-ish. They can sabotage 2, the medium group can sabotage 3, and the fast group, even at age 6, is already sabotaging 4. So eventually, the slow group does get to be able to sabotage 4, but it doesn't start by being able to sabotage 4. So you can see that there are important differences between these 3 groups. And the sabotaging group, so this group here, the slow group, constitutes about 7% of our sample. This isn't a prevalent study, so you have 7%. We don't know whether that's representative or not. I'll come on to a prevalent study in a minute. But does it predict how well these kids are going to learn arithmetic? So we tested them on age-appropriate arithmetic using the clusters defined in kindergarten. Okay? So we're sticking to the same clustering that the child was in kindergarten. So in kindergarten, this is single-digit addition. You can see that the slow group is getting about 30% right. This isn't timed, this is just untimed. Medium group's getting about 60% right, fast group's getting 80% right. What about older, when they get a bit older? As you can see, this is on 2-digit arithmetic, addition, subtraction, and multiplication. The slow group is still way behind the other 2 groups. And 3-digit addition at 3-digit arithmetic at 10 years, you can see the slow group is still having trouble. What this means is that you can use this very simple test. Educational psychologists, neuropsychologists, teachers can use this very simple test to identify which children in kindergarten are likely to have trouble learning arithmetic as they get older, and they can take the appropriate pedagogical steps to try and help them. So it's important to distinguish dyscalculia from other types of arithmetical learning difficulties. And in one study that we did in Cuba, which was a prevalent study, it took a universal sample of one district of Havana, so that's 11,500 children, and we sampled from that, that's the reference sample, we sampled from that 11,500 children in an appropriate way, 6 to 9 6 to 16 years old, I think. And we individually tested with a timed test, timed arithmetic, timed dot enumeration, timed number comparison. We individually tested 2,000 kids. And one of the things that we thought was important was to distinguish between kids who were just slow at doing calculation from those who were slow at doing calculation plus those who were bad at doing dot enumeration. And there are about 9% of them who were slow at calculating, and so these would be what I would call dyscalculics, slow at calculating and bad at numerosity processing. That's about 3.5%. So the core deficit in numerosity processing is what distinguishes dyscalculics from other forms of poor numeracy. And you can use this basic measure. It's very easy to do. And in fact, there's a product called the Dyscalculia Screener, which we published over 10 years ago now, which you can buy. It's expensive. That's not my fault. And you can use that to test your kids. It's got norms and everything. And for dyscalculics, numbers make little or no sense. They learn arithmetic mainly by rote. They're typically slow and ineffective at learning. Counting is usually okay, and they like to count if they possibly can. And they're very slow to respond to intervention, partly because the intervention is not really designed for dyscalculics. Is this condition inherited? So let's have a look at the heritability of numerical abilities. So in our big prevalence study, there were, of the dyscalculics, about 2.5 times as many boys as girls. So that shows that there's a genetic effect. In twin studies, you find there's quite a significant genetic effect. I'm going to say a bit more about twins in a minute. There are also interesting genetic anomalies, particularly X-chromosome disorders, and in particular Turner syndrome, where you can have intact language and reading, but severely impaired calculation. In fact, I think every Turner female that's been tested is bad at number tasks as compared to other sorts of cognitive tasks. As Josep mentioned, there are co-occurrences with other conditions, so we did a summary of co-occurrences and published it recently. And important to notice here that there's quite a large genetic effect with large twin samples, which is specific to number tasks. And also there are important environmental effects as well. So if you think about, I'm going to talk about the brain in a minute, if you think that this is due to some brain abnormality, there can be genetic reasons for brain abnormalities in children, but also other reasons for brain abnormalities too. So this is non-shared environment having an effect on dyscalculia. Here's just a little study we did on Turner syndrome years ago. These are reaction times for Turner's syndrome doing single-digit addition, multiplication, and subtraction. And they're slower on all these tasks than controls. Now, timing is really important here because there's a difference between, I can't stress this enough, there's a difference between a child, or if you ask a child, what's 3 plus 5, and the child goes 8, the child is getting it right. So on accuracy, the child is getting it right. But if you ask another child, what's 3 plus 5, and the child says immediately 8, there's something different going on in the head of the second child from the first child. So timing is a very important, as we all know from experimental psychology, an important diagnostic. These Turner females were also slower to do dot enumeration. This is Turner in white. This is controls in dark. And also doing number comparison, they're slower, but doing the size comparison task, which of these 2 digits is taller, they were not affected. So they can make decisions just as quickly as controls, unless it involves numbers. Just let me tell you briefly about a twin study that we're doing. We've got about 160 twins. We've given them 40 behavioral tests. We've done structural scans for all of them. We've excluded them on the basis of gestational age, some extreme cognitive outliers, and of course, if we can't analyze the brains because of motion blurring, then we get rid of them. We assessed zygosity on the basis of molecular genetic methods. We've published some of this, and we're in the process of publishing some more. So because there were 40 tests, what we have to do is a bit of data reduction. So we did factor analysis, and the biggest factor, factor 1, which I'm calling number processing, included 1 numerical operations, addition efficiency, that takes into account both accuracy and speed, subtraction efficiency, multiplication efficiency, and dot enumeration. There were 3 other factors which accounted for a smaller proportion of the variance. And then we calculated for each of the participants the Mahalanobis distance on the basis of factor 1. That's just a way of measuring outliers from the sample mean on the basis of several dimensions. So let me just briefly tell you about the heritability of our cognitive measures. So all of these measures are significant: timed addition, time subtraction, time multiplication, and dot enumeration. Of course, you can see there are also significant effects of shared and unique environment. These abilities are heritable, moderately heritable. There are other factors as well. And then we did a cross-twin, cross-trait genetic correlation with dot enumeration. So how correlated is dot enumeration with these other tasks, comparing monozygotes to dizygotes. So it tells you how heritable the relationship is between dot enumeration and arithmetic is, and you can see these are all significant correlations, particularly addition, and these are significant as well, they're moderate, and also finger sequencing. I have a whole story about fingers, which I'm not going to go into now. So what about the neural basis of these individual differences? Now, we did a task here, I'm just giving you half of the task that we did, to look at whether there's a special area in the brain for numerosity processing. So the task in the scanner, this is adults, was, is there more green or more blue? Okay? And so we took the activation for stimuli like this, where there's really just one object with varying amounts of green and blue, and this stimulus, where there are distinct objects, rectangles of blue and green. So we subtracted this activation from that activation to see what was left. And of course, if it's this, if you're just doing an estimation of how much, you do that subtraction from that subtraction, you'll get nothing. Except, of course, this is a different type of visual stimulus, and we got some areas in occipital lobe which were different for this compared to that. But what was interesting was in the interparietal sulcus, that's one view of it, this is another view, these two areas here, what you found was that activation was modulated by the ratio of blue to green rectangles, having already subtracted the equivalent continuous stimulus there. So this is an easy one, 14 versus 6, 14 green versus 6 blue. So you don't get much activation there, but if it was 11 green versus 9 blue, you'd get more activation here, but not in the occipital lobes. And I've just connected these to a map of the arithmetic network from another team, and this has been very reliably shown in many, many other studies since, including by some members of this team. Left and right parietal lobes, particularly on the left, and some frontal activation as well. So the numerosity processing area is part of the arithmetical network. And if you look at brain areas which are abnormal in dyscalculics, you find it is this area, particularly in the left here. I mean, some people have found it in the right as well. I'm not going to show those today. So the same coordinates in Isaac's original study of dyscalculia and in our twin study of dyscalculia here. So you get abnormal grey matter density in these two areas corresponding to the numerosity processing area. And this region of interest is heritable. So grey matter density in this region of interest is a heritable factor. And the region of interest plus the number factor, that is the Mahalanobis distance from factor 1, if you can remember back that far, that's also heritable as well. So you get this heritable connection between grey matter density and your ability to do arithmetic. Of course, the relationship between genes and behavioral tests is complicated. This is just a picture of how genes might affect different brain areas, that might affect different cognitive processes, that might affect different behavioral tests, all of which interact with the environment, including things like nutrition. Just to show that we don't take a simple-minded view of these relationships. So how do we educate developmental dyscalculia? Well, from neuroscience to education, there is no simple logical pathway. You have to identify deficits and strengths. You have to use established pedagogical principles. You have to use ideas from the best practitioners. And you have to use, and you can use, we use, technology to capture and test some of these ideas. So Josep kindly mentioned this book here, Dyscalculia Guidance, which is based on the kind of theory I've been describing and the kinds of activities that you can use with kids in order to help them strengthen numerosity processing. There are also some adaptive technologies that you can use. There's number race, developed by Stanislas Dehaene and colleagues, Calcularis, developed by Karen Kuchian, which you can buy if you go to that website. Meister Cody is very nice, much more graphically sophisticated and actually intellectually more sophisticated set of games that you can use, developed by a team at the University of Münster in Germany. We have some free games developed by my colleague Diana Lorillard, and there are 5 or 6 games here that you can play, or you can get your dyscalculic learner to play. There's one that's now you can use on your laptop, not on your laptop, you can't use it on your laptop, you can use it on your tablet or your iPhone or your Android phone. And let me just go through one of these interventions and how we try and combine a neuroscientific theory with pedagogical principles. Okay, so we start with regular dot patterns from 1 to 10. And so we link the pattern to representations on the number line and to a written digit and to the sound of the digit. And the aim is to help the learner recognize rather than count dot patterns, because the dyscalculic likes to count, because that's a reliable, not a stupid, but and because it's a reliable procedure to get the right number. And it enables them to see regular patterns, and then we get them to see regular patterns within random collections. I'll show you how that works. And we use learning through practice, not through instruction, which is an important pedagogical principle. Okay, so this is kind of a PowerPoint mock-up. You can play the game yourself. So it's very simple. The screen contains no numbers that aren't relevant to the task. So there's also sound that goes with this. How many are there? And so you type in, let's say you type in 4. What happens if you type in 4? It says, you typed 4, this is your line, and and it counts down 1, 2, 3, 4, and then it counts down the correct number onto there. So concept learning through contrasting instances, plus it's giving you informational feedback. You not only got it wrong, but you can see how you've got it wrong. You can see that you underestimated the number of dots in the array, or you didn't know that 4 just meant that number of dots. So then what you can do is you can fix your line, that is, you can correct it. It was all really simple stuff, but we think it's very important. And this is a pedagogical principle known as constructionism, based on the work of Seymour Papert, where it helps the child if they can construct the right answer. So just saying that you're wrong and giving them another go at some other item is not helpful. So then you can try subtracting, or you can try adding, and if you add, you get it right. And here the pedagogical principle is reinforced associated representations. Those of you who've done any educational psychology will recognize these principles. So how many are there here? Okay, 4, you get it right this time, so you reinforce and build on what has been learned. How many are there? This time we try and get them to do it quickly, focus attention on the salience of numerosity rather than on the sequence. So, okay, so you get them to speed up their recognition. Then you can see here there's some familiar patterns within the random pattern. And so you can then get the right answer. So here's a little bit of data. Because it's adaptive, what you're getting is this sawtooth pattern, because as they get better and faster, you then make it more difficult for them. So the reaction time in seconds goes up, and then they get better and it goes down. And so you get that sort of pattern. And these are year 4, these are 10-year-olds. And at the bottom here, these are kids without dyscalculia. You can see they're much, much better. They're all doing all these tasks within 2 seconds. Okay, so here's the take-home message. You've seen it before, and I'll just repeat it. There's a specialized neural network for numbers and arithmetic in the parietal lobes. Acquired dyscalculia is due to damage to this network, and this can affect the patient's ability to live an independent life. And so you should try and find out what's wrong and try and fix it for them. Developmental dyscalculia, the network does not develop normally because the number module is defective in some way. This is a serious handicap. It's more of a handicap in the workplace than poor numeracy. And men and women with poor numeracy have poorer educational prospects, earn less, are more likely to be unemployed, more likely to be in trouble with the law, and more likely to be sick. Both acquired and developmental dyscalculia required specialized intervention. Thank you for your attention, and you can go to the website to get the papers, and thanks to all these people for helping me with the research. Thank you very much.